Hello everyone. For those of you who don't know me, I'm Angelica. I'm one of the instructors for this course this semester, and I will be your guide through chapter 3, which has to do with determinants. Before we give the definition of a determinant, I want to provide a very teeny quick motivation for why we care about determinants. So let's look at 2 by 2 matrices for a second. Suppose A, B, C, D is a 2 by 2 matrix, okay? And suppose we want to compute its inverse. Now in chapter 2, we're given a formula for the inverse of a 2 by 2 matrix, and it is following. So A inverse is going to be given by 1 over AD minus BC. And then we have the 2 by 2 matrix, which is given by D and A on the diagonal minus B and minus C. And then if you compute A inverse A, this is the same as A inverse, and it gives you the identity. Nice. Now, an important role here is played by this quantity, like this quantity over here, which, as you might remember, it's called the determinant of A. So determinant of A is defined for 2 by 2 matrices as AD minus BC. Why is it important? Because, well, we're told that if the determinant of A is not equal to 0, then A is invertible. While if determinant of A is equal to 0, then A cannot be inverted. Okay, A is not invertible. So there seems to be a connection between the concept definition of determinant and invertibility of matrices. And, well, why is it? One easy answer is, well, because if the determinant of A is equal to 0, we are in trouble with this formula, right? We cannot apply the formula because we have to divide by the determinant. And if it's 0, we cannot divide by 0. That's a very well-known rule in mathematics, so we're in trouble. But, well, there's a more intrinsic reason, if you want, and it's the following. So suppose you want to reduce. Suppose you're given again this matrix A, B, C, D, and let's assume that AD minus BC, which is the determinant of A, is equal to 0, okay? And for the sake of this argument, let's assume A is not equal to 0. It doesn't change anything, and everything carries out, but I don't want to be in trouble having to exchange rows. So let's, for the sake of this argument, let's assume A is not 0. And let's try to find the echelon form. Let's try to row reduce A. So if we want, so echelon form. And remember, all we know is that A is 2 by 2, capital A is 2 by 2. A is non-zero, and then we have this information over here. Okay, so I choose my first row to be my first row of the echelon form. A is my first pivot, and then how do I get a 0 below A? Well, let's see what happens if I do the following. So I'm going to do replacement, and I'm going to replace the second row with D times the first one minus B times the second one. Okay, so what does this give me? Well, it's dA dB, and then the second row becomes minus BC minus BD. So when I add these two rows up, what do I get? Well, here I clearly have a 0, and then here I have a 0 as well. Why? Well, exactly because of this condition over here, right, that we assume the determinant is equal to 0. So this also gives me a 0. Therefore, the echelon form of A is going to be, so the echelon form of A of type, well, AB 0, 0. So what can we say about the columns of A? Does this implies that the columns of A are linearly dependent, which is one of the equivalent conditions to A being invertible, not invertible. So if I discover that the columns of A are linearly dependent, that tells me right away that A cannot be inverted, that has no inverse. So A is not invertible. Okay, so hopefully this is a more geometric answer to the question, why is determinant connected to invertibility of matrices? Well, you can really, if the determinant is equal to 0, really you can see that there's a linear relation between the columns. Hence, you get the result. Now, this seems really nice. The next question is, can I generalize this to 3 by 3 matrices, 4 by 4, or n by n in general? So can I compute the determinant of an n by n matrix? And of course the answer is yes. And here it is how the determinant is defined for an n by n matrix. So there's not really an easy way to describe this. You have to go through the formula, but what is it? So a matrix is given by its entries, aij. So small aij is the entry in the ith row, jth column. So what I'm doing here is I'm picking the entries in the first row. Okay, so this is the first entry of the first row, second entry of the first row, all the way down to the last entry in the first row. And then I'm multiplying these entries, so real numbers, by the determinant of a matrix. Capital A11, capital A12, A12, etc. And then I'll define these matrices in a second. And then I'm taking a sum, but this sum it has alternating signs. Okay, so I start with a plus, then I subtract A12 times the determinant of A12, and then there's a plus, and then there will be another minus, plus, minus, until the last sign, which depends on n. Okay, and well, there's a compact way to write this down, which is this summation over here. Okay, so who are matrices capital Aij? Well, this is the matrix that I get from the original matrix A, removing the ith row and the jth column, and then I compute the determinant. And if you like look careful here, I have this assumption n equal to 2 or greater than 2, larger than 2. Why is it? Well, because if you have, well, if A is a 1 by 1 matrix, then really A is a real number, right? It has one column, one row, so it really has one entry. And in this case, we define determinant of A to be, well, the only entry, the only real number you have. So it's going to be A. Okay, now, just a bit of notation. Okay, I'm going to rewrite the formula for the determinant a bit differently. So remember, okay, determinant of A, we said is going to be A11, and then there's a sign. I'm going to write it like this, when 1 and 1 refer to the entry that I'm looking at. And then there's the determinant of A11, and then there's another minus. Sorry. A12 minus 1 plus 2, determinant of A12, all the way up to A1n, and then again this sign, and then the determinant of A1n. And for the sake of notation, I'm going to take all of this, so the determinant and the sign together, okay? And I'm going to give a name to this. So these are called cofactors, okay? So I'm going to use a C and then denote it by the same indices that I have for A here. Okay, so this would be C11, and this is C12, all the way up to C1n. And they are called cofactors. Okay, each of these determinants together with its sign, okay, which can be a plus or a minus, are called cofactors. And I'm going to call such a thing, the whole expression over here, a cofactor. So this is a cofactor expansion along the first row of A. Okay, because the entries are the entries of the first row, and then they're multiplied by cofactors. So this is a cofactor expansion. Now let's check that this formula over here actually gives us the determinant of A for a 2 by 2 matrix. Okay, so, well, if A is a 2 by 2 matrix, right? So again, A is going to be A, B, C, D. And what does the formula says? Well, the formula says that the determinant of A is given by, as we said, we look at the first row, we pick the first entry, A, and multiply by the matrix that I obtain if I, so okay, let me write down. So this is A11, and then remember there's a minus. Then I look at the second entry in my first row, so this is going to be B, and then I have, oh here, I forgot determinant. And then I have the determinant of A12, okay? As we said, whose A11 is the matrix that I get from A when I remove the first column and the first row. So if I remove the first column and the first row from here, what do I get? Well, I'm left with D. So this becomes A, and then the determinant of this 1 by 1 matrix, which is D. And then I have a minus B, and well, now I need to get the matrix which I obtain removing the first row and the second column. So what's that going to be? Well, it's going to be C, okay? Okay, determinant. And then remember, we said that if we have a 1 by 1 matrix, then the determinant is exactly the entry, the single entry that you have. So what is this going to be? Well, not surprisingly, this is AD minus BC, which checks out with what we expect for a 2 by 2 matrix. Okay, so just to be sure we understand, well, let's do an example with a 3 by 3 matrix. So for a 3 by 3 matrix, let's write down the formula again, okay, just to make sure that we know. So, well, following what we said below, above, determinant of A is going to be first entry in the first row times, well, this time, which is going to be a plus, and then the determinant of A11 plus A12 determinant of A12 plus determinant of A3. And this is it, because we are dealing with a 3 by 3 matrix. So the last entry would be the third entry in the first row. Okay, so if we have now a real matrix, let's say 1, 2, 0, 5, 4, minus 2, 0, minus 1, 0, then let's compute this determinant. Okay, so finally a real example. What do we need to do? Well, let's look at the formula that we have above. Determinant of A is going to be A11. So who's A11? A11, it's the first entry, so it's going to be 1 times minus 1 to the second power, and then there's the determinant of the matrix that I get if I remove the first row and the first column. So it's going to be 4 minus 1 minus 2, 0, right? I have to remove the first row, I have to remove the first column, I'm left with this matrix here, okay? Nice. And then, well, let's keep going. We get second entry is equal to 5. And here we have the determinant of, I have to remove first row, but the second column, okay? Second column. So if I remove this, what am I left with? Well, it's 2 minus 1, 0, 0. And then finally, going here, because I don't have space, well, oh, well, I do. We have a 0, right? Last entry in the first row is 0, so we don't really care what follows. It's going to be 0 nonetheless. So this is it. And then we have to compute this. So minus 1 to the power of 2 gives us a plus. And then there's 1, so we just need to compute this determinant. And now we know how to compute determinants of 2 by 2 matrices. So this is going to be 4 times 0, and then you have minus minus 2 minus 1. And then, well, minus 1 to the power of 3 over here, it gives us a minus. So this is minus 5. And then again, we need to compute the determinant, but this determinant will give you 0. So this is 0, and then plus 0, which gives us 4 minus 2 times 1, which is 2, which gives you 2. Okay, so the determinant in this case is actually, oops, supposed to be minus 2. Sorry. This is 0 times 4. So this gives you minus 2. Okay. And this is how you would compute any determinant. So it's basically, if you look at this formula, it's really recursive, right? Every time you reduce to a smaller matrix until you get to 2 by 2 matrices, and then you know how to compute those determinants, and that works very easily. Okay, let me stop here.